We have here, both people call this Lagrangian. As I said, it's best to copy the notation of the physics community. It's always the best notation. Now I want to indicate some really interesting point. A key confusing point is, at least for me at the beginning of the subject, is that gamma depends on the parameterization. Right? Gamma is a mapping from an interval to a manifold, and if I apply diffeomorphism, let me write it here. As a picture, you have a manifold, and here's this image curve gamma, and it's a mapping here from A to B, and if you have this as a mapping gamma, and if you apply diffeomorphism, you should always have this picture. I tell the beginning students, always draw this picture of change of variables. This is the right picture of change of variables, say phi. If you have a diffeomorphism from some other interval to AB, you get the same curve. Right? This curve here is gamma composed of phi. It's really the same curve. And so, also as you learn calculus, it's a good idea to choose a particular parameterization. And if this curve is smooth, which means, in particular, we're looking at a local situation now, if the curve is smooth, the velocity vector never vanishes. It may increase and decrease and increase and decrease and so on. But what we can do is choose the parameterization by arc length. Right? You can do that. Right? In other words, you have a change of variables. This is maybe an S space and this is a T space. You make this change of variables from T to S, and now S parameterized by arc length. This means the stupid thing that the length of this thing is always 1. Right? That's what it means. Right? That means that these two integrals are up to a constant the same. Okay? This means that the physicists, as usual, are right. We don't need to look at the square root of this thing. We can look at the Lagrangian and the action, because it's the same for R. Yeah. You don't like that.
How would you choose such a parameterization? Like, what's different? What makes the how does the parameterization change the length of, like, the norm squared G? curve.
She's very, very asking these terrible questions, which I'm not mad. I'm just resting because you tell me this terrible question. How does changing the parameterization have anything to do with this? It certainly has to do with a curve. It changes the curve. Come on, a curve is a map, is a map, is a map. I've said a million times, a curve is a map. If you don't write a curve, if you think of a curve as just some image guy running around having fun, you're wrong. A curve is a map. Now, this means, for example, if you're driving Formula One, the first Formula One race will be in Melbourne this weekend. Oh, today's Friday. Tomorrow the trials in Melbourne. I don't know, it'll be very interesting to see if Leclerc does well with Ferrari. I don't know, I watched it. So, if you have Sebastian Vettel, you maybe know Sebastian Vettel, he's the German great driver, goes slow around the first thing and then goes incredibly fast along the back, and his Ferrari goes 330 and then comes to the slow curve, sometimes 60, and then so on. He's changing his velocity, but the curve is the curve is the curve is the curve. In terms of the image, right? So you should take the bloody parameterization out of the picture, right? You should parameterize by unit velocity, or constant velocity at least. That would help. So Vettel has a certain non-constant velocity going around this curve thing, and I will get there and drive. No, I can't drive. He will go 330 in here, 80 and so on. But I will drive, no, I won't make it, but I would drive maybe 220 or 2, something like this. I used to have a fast car. And it's clear, right? So we take parameterization out of the picture and make unit parameterization, which we can do. Right? The parameter is the arc length. So the point S that parameterizes the point on the curve is the length from the 0 point to that point. Yeah? Okay. And now Maria asked this question, what happens, it should not, I'm answering your question now, or making precise your remark. I mean, you believe it, right? You better believe it, because we're parameterizing length. And it should not have to do with parameterization. And this is a trivial calculation. You just put in, change the variables and do the calculation. You've probably done this before sometime, right? So that's great. So that means that the length functional and the energy functional, or the action functional, are the same on essential curves. So this means we go to minimizing the energy integral, or action integral. Right? And it's a heck of a lot better to do that with that square there, for one thing, and it turns out, conceptually, it's also better. So this is the thing to consider. The energy integral or action integral. So again, the physicists were right. They know that. Okay, so we do, we begin as a child. And I teach many courses, including courses for children. For example, Applied Calculus 1. Well, and then they go on to make money, and I'm a poor high school college teacher, and so on. They go on to the finance industry and make millions. Right. Or high school. German people know all about this high school stuff. We begin as a child, find, set. So we have a function. Here's x. and here's some function here, and we're looking for this point here. Here's x, and this should be the derivative of x equals, so this is a function f, and you try to find f, derivative of f equals 0. Right? Now there are always two things, there are no Germans here today. Oh yes, the columns are German, sort of. Yeah. It's called Kurvendiskussion, yeah? You discuss curves, and the first thing you do is you find the zeros of the derivative, and then you find the endpoints, because maybe the minimum or maximum is taken at the endpoint, and then you check all three things and try to find the minimum, right? Right. But for a bit older child, you check this thing second derivative out, right? There's a good reason to check this second derivative out, right? You write down the Taylor expansion of the function to third order, and you see that the second derivative, if it's non-zero, will tell you what's going on, right? If everything vanishes, you have something vanishing in third order, it's very delicate, right? But you write down the Taylor series to second order, and you get that. And if you know that this thing is positive, then that means a minimum. We will not do this here, but in fact, the second derivative test here, but in fact, you can do it. Okay? We will do only the first derivative, we only need the first derivative here. Okay? So we need to find critical points of the energy function. Critical points mean that this thing is 0. I have to talk here, but I will just say what I'm going to talk about this afternoon. So the general notation will be this. We will have an energy functional defined on some curve, gamma. I'm trying, so notation, I suggest you look at Arnold. And here, his book on methods of mathematical physics. Is that what it's called, method of math physics? Hang on.
Classical mechanics.
Methods of what?
Classical mechanics.
Classical mechanics? Probably classical mechanics. Mathematical methods of classical mechanics, yes. And his notation, I will try to copy his notation. Maybe he calls this U. I'm not sure. I can't remember. There's always, for some dumb reason, a half here. The curve is defined on AB of something L, U, U prime, and T, dt. Does that look like good notation to you? Okay. Yes.
But, so if we say that so we choose a parameterization by an arcane, so the energy shouldn't be just the integral from A to B of 1 dt, and then
That's what it is.
And then this b minus a over 2, right?
That's right. So I don't care about the half.
So what?
Well, if I minimize half of something, it's the same as minimizing something.
Yes, but isn't that constant? I mean, you just choose your integral, and then that's the energy.
That's a trivial integral. It's a terrible thing, right? It's a completely trivial integral to compute, the integral of 1. Yeah, but but you don't know the curve parameterized by arc length. Excusez-moi. Nobody knows this curve. We're trying to find the curve, actually, and you have to solve this ODE to find the curve, and then parameterize, yeah? Okay? So it looks crazy, but in fact, you see the point, right? Yeah. So this is the notion. This is the action or energy. U is a function of t, and this is called the Lagrangian. And now I will stop the lecture this afternoon, but let me warn you. Let me just tell you how confusing it is for mathematicians to look at this. This looks like a function of t. This looks like the derivative of the function of t. It is not. It is the variable u prime of t. Yes? Which, when you have a specific curve u, you put in the derivative for that variable. You got it? Do I need to... This is a very confusing thing that these people put on us, but they do it not intentionally to confuse us, it's just to simplify matters. Those are three variables, u prime, and t. Okay? If you like, you can think of one of those variables as potential energy, and another one of those variables as kinetic energy. Right? Measuring in a system. And then you put a curve and then it measures it. Okay? Those are variables. They are not, when I compute it at certain points, when I put in a function, I will differentiate, right? Okay? So this is confusing. Maria, you will be really confused by this. Okay? When you read Arnold, you have to read Arnold. It's one of the most beautiful books you will ever read. These two books, you know, I seldom read books, but these two books I have read. It took me 1 month to read the first 80 pages of the book, and another 2 or 3 weeks to read the rest of about a 500-page book. The first 80 pages are serious classical mechanics in the sense of physics, and it's difficult. I strongly suggest you do it. Okay? So these are variables. This is the Lagrangian, and you're trying to minimize, you're trying to find the critical points of this thing. So we're trying to find the points where, whatever that means, the critical points of this thing, and I'll do this afternoon. Just find the critical points of this thing. This gives us the Lagrangian equations of classical mechanics, and this gives us, in this case, the Lagrangian equations of the geodesics, and using the Legendre transformation, which I will introduce this afternoon, this gives us the Hamiltonian equations of geodesics, or classical mechanics, which embeds all of classical mechanics in symplectic geometry, one of the most important modern subjects of mathematics. Let me say it again. Lagrangian, Hamiltonian, symplectic geometry. You have a question?
Yeah. It's not very clear to me why or how this way we define a geodesic is based on the metric, whereas the previous way is based on the connection, and they should not be related.
Let's, you hear what he's saying? It's a very good question. We have two definitions, so let me just, since I've gone over, let me go over a little bit more. So, critical points. What is called critical? Of the energy integral, so let me just write it as above. They are called Riemannian geodesics. For For the obvious reason, because I use the Riemannian, this is your point, I use the Riemannian metric to define those geodesics, right? We will see, maybe I put in here, thank God, if the answer to your question is that the ODEs are the same. On the action integral, the same. As the ODE for the connection integral. And the point that you're making is that we now have an ODE that really, in some sense, generalizes the naive ODE for geodesics, right? Or for any connection. So in some sense, it shows you really the right thing to consider as a connection, right? From the point of view of the ODE. Okay. It's very interesting. Okay, see you this afternoon.